Okay, so hello and welcome everyone. We are live on this particular channel of Unacademy JEE English, and in this session we are going to revise electromagnetic induction in a very short manner. It will take approximately 1 to 1.5 hours, and in this session we'll completely see each and every concept of this electromagnetic induction. So this is not a detailed one shot. This is not a one shot which will take 5-6 hours. This will take only a very less time for you, and it will revise each and very important concept in a very important or very effective manner. So let us start from the very beginning, and let me tell you one thing. If you are planning to buy a subscription, if you are planning to do something bigger in your life, then you must have this particular subscription in just 4499. Use the code SVJEE so that you can get the maximum discount, and you can get all kind of batches for the, if you are preparing for, if you are a dropper, if you are in 11th, if you are 12th, if you are any one of these, then you have all these batches for you. Just link is in the description as well as in the pinned comment. So let us start from the very beginning. Let me tell you what is the today's goal. Okay, I will, don't worry, okay, we will upload all the things. Okay, no problem. So what we are going to do in this particular session, we are going to revise all these concepts. Either it is magnetic flux, induced EMF, motional EMF, induced electric field, or self-inductance, mutual inductance. All these concepts we are going to revise in this particular session. So first of all, let me tell you, this chapter is the application of some important chapters like magnetism. If you have studies magnetism from me or anyone, so then this chapter is kind of an extended version of magnetism. Then what you are doing, like suppose that you have studies electrostatics or magnetism, then this chapter is like a continuation of electrostatics and magnetism. In electrostatics, we saw that the charge is at rest, then we calculated the force on the particular charge. Then in the magnetism, we saw if a charge is moving with a constant velocity, then what is the force experienced by that particular charge. But in this session, we are going to see that if a charge is accelerating, if a charge is moving with a variable velocity, if charge is moving with decreasing speed or increasing speed, then what will be the effect of the particular thing, or what is basically the electromagnetic induction. What is induction, we are going to see in this particular chapter. Okay, so let us start. Okay, so let us start with magnetic flux. What is magnetic flux? Let me tell you. First of all, if we have a loop, if we have this particular loop, circular loop or rectangular, whatever it is, so first of all, if it is a loop and it is kept in a magnetic field, it is kept in a magnetic field, then there is something like, there is a magnetic field B naught and the area is A. So first of all, let me define the magnetic flux for you. If this loop of area is kept in the magnetic field B, then the flux is basically the number of field lines passing through the unit area. So we can define the flux phi B, that is equals to B dot A, or we can write it like BA cos theta, right? BA cos theta. So magnetic flux is basically depending on three things. First of all, magnetic field, which is B. Secondly, area. Thirdly, the angle between magnetic field and area. So first of all, if the magnetic field, suppose that is in this direction, this is the magnetic field's direction, this is the magnetic field's direction, and this is our area, this is our area, and this angle is 30 degree. This angle is 30 degree. So suppose that this is magnetic field is B naught, area is A naught, and we have to calculate the value of magnetic flux passing through this particular area. So what we will write particularly, phi B, which is the magnetic flux, that is equals to, what is magnetic field? B naught into multiplied with area A naught multiplied with cos. What is cos? 30 or something else. So first of all, let me tell you one thing, that you will have to take the area vector or some theta. Theta is between the magnetic field and the area vector. So what is area vector? Area vector is perpendicular to the surface. So this angle is theta. This angle is theta. So if this is 30 degree, this will be 60 degree. So cos 60. Cos 60 means 1 by 2. So this will be B naught A naught by 2. So keep this thing in mind, that theta is the angle between the magnetic field and area vector, right? Okay. So next thing, if we have suppose that this is a loop and this is magnetic field, and if magnetic field is not constant with the time, magnetic field is changing, this is B, but B is changing, B naught T. Suppose that magnetic field is increasing with time and the area is A. So simply we saw some effect of this particular thing, that if the magnetic field is changing with time, then we saw a particular thing, that there is a small current flowing through this particular cross-sectional area or this particular loop. So what we saw, if there is a changing magnetic field, then there is a current in the loop. Similarly, if we change the area, then again we saw a current in this particular loop. Secondly, the thing is, if we just rotate this particular loop, suppose that we have this loop, let me show you some kind of thing. Suppose that this is a loop, right? This is a loop, okay, and this is like this, and magnetic field is in this particular direction, in the vertical direction, and this is rotating like this. This is rotating like this. Then also we saw that there is a current in this particular loop. So we saw three things, that if magnetic field as well as area as well as the angle between the magnetic field and area is changing in this particular scenario, then there is a small current which is flowing through this particular loop, right? Now listen to me very carefully. If all these three things are changing, it means we can simply say we saw that phi b, that is equals to BA cos theta. It means if B is changing, A is changing, or theta is changing, all these three quantity one by one is changing, then the flux is changing. And if there is a change in flux, then we can say that there is a small current flowing through this particular loop. And now we will just make it like a story, something like this, like something like this, that B, A or theta, if these things means phi, if it changes, then there is a, now I said that there is a small current, right? But listen to me very carefully. If there is a small current, current cannot be there because of some potential difference. If there is no potential difference, there will be no current. So if there is a current, it means there will be a potential difference, and that potential difference is called induced EMF. What is called? Induced EMF. So if all these three quantity, any one of them changes, then there is a induced EMF. Induced EMF. And because of that induced EMF, there is a current which is called induced current. Okay. So just keep this thing in mind, that if B, A or theta, any one of these quantities is changing, it means induced EMF is coming, and because of that induced current is coming. Now we have two aspects here. If there is a induced current, then there are two aspects of the current. First is, what is the magnitude of the current, how we will calculate that particular current. Secondly, what is the direction of current? It is clockwise. Suppose that this was the loop now. This was the loop. So where is the current? Current is clockwise, anti-clockwise. There must be some direction now. So there are two aspects of this current. One is magnitude and second is direction. Now, to calculate these things, magnitude and direction, there is a law which is called Faraday's law. And Faraday gave two laws, Faraday's first law and Faraday's second law. So first law, what first law says? First law, which gives the magnitude, and second law, which gives the second law, which gives the direction. This is also called Lenz law. So what is first law? First law says that if there is a change in the magnetic flux, then the induced EMF is written like this. Induced EMF, that is equals to the rate of change of magnetic flux, that is equals to d phi b by dt. If there is a one circle in the loop. Okay. Now this is a magnitude, but there is an extended negative sign here. What negative sign represents? Negative sign is just the representation of this second law, or we can say the Lenz law, right? Any doubt till here? Okay. So we have till now what we have learnt? We have learnt that there are two laws. First is first law, and obviously first law. And first law gave us the magnitude of the induced EMF. And if we have calculated the induced EMF, we can calculate the current as well. Because if we know the voltage, we can calculate the current. If we know the resistance, so there is the current also. I is equals to E upon resistance. So this is the basically first law of Faraday, right? Now this negative sign represents the second law. This is the presence of second law, and this is showed by Lenz law. What Lenz law shows? It simply says that if you have a loop, if you have a coil in a magnetic field which is changing with time or the flux is changing, then current is produced in such a way, just listen to me very carefully, current is produced in such a way that it opposes the cause, by which it is being produced. Now, we had this loop. Now listen to me very carefully. If you have any confusion in Lenz law, then this example will just solve anything for you. Now, this is the magnetic field, and magnetic field is increasing with time. Now, this is the loop. If magnetic field is increasing and magnetic field is inside. Now, listen to me very carefully. Listen. Okay. Class started at 2:30. Okay. So, listen to me very carefully. Now, if the magnetic field is increasing, it simply means magnetic field is inside. Let me tell you. This is the magnetic field. Okay. This is the magnetic field inside. Now, if inside magnetic field is increasing, it simply means that the current will be produced in such a way that it will oppose the cause by which it is being produced. So what is the cause? Cause is the increasing magnetic field which is inside. It means current which is being produced will be in such a direction that it will oppose this inside magnetic field. So magnetic field is inside. So what current will try to do? It will oppose this magnetic field. So current will try to produce in such a way that magnetic field is outside. So if the magnetic field is outside, means current is in anti-clockwise direction. Current is in anti-clockwise direction. Got it? Any confusion till here? So in this particular loop, current is in anti-clockwise direction. Similarly, what if I said this is the loop, this is the magnetic field and this is the loop. Now inside the magnetic field is decreasing. Since the magnetic field is decreasing, now what current will try to do? What is the cause? Cause is the decrease. Just look at the cause. What is the cause of this induced current? So cause is the decreasing magnetic field. So if the magnetic field is decreasing, it means current will be produced in such a way that it will try to increase the magnetic field. So if inside the magnetic field is decreasing, it means the current will produce in such a way that it will try to maximize the magnetic field. It means magnetic field will be inside. And if the magnetic field is inside, what is the direction of our induced current? It is simply clockwise. It will simply clockwise. Done. Yes, this is the same rod. Okay. Any confusion till here? Should we move on to the next thing? Definitely we should move on to the next thing. Now look at this example. The magnetic flux we have been given, the magnetic field is a closed circuit of resistance 20 ohm, varies with time according to the equation phi is equals to 7t square minus 4t, where phi is in Weber and t is in seconds. The magnitude of the induced EMF at t is equals to 0.25 seconds. So very simple question. Phi is given as phi is equals to 7t square minus 4t. Now we have to calculate the magnitude of induced current. So how we will calculate the induced current? First of all, we'll have to calculate the induced EMF. How we'll calculate the induced EMF? E is equals to d phi by dt. d phi by dt. So just differentiate it. 14t minus 4. Now at t is equals to 0.25, means if we'll put this E is equals to 14 into 0.25 minus 4. This will give us the value of induced EMF. So 0.100 means 24. This will be 2, 7 minus, means it will, or there is a minus sign. No? There is a minus sign also. So this will be 7 2s are 40, 7 minus 7 by 2. 7 by 2 minus 4. So this will be simply minus 1 by 2, n plus 1 by 2. 1 by 2. This is the induced EMF, means in volt. Okay. Now, again, we have to find the induced current. So I is equals to what? I is equals to V upon E upon R. E is equals to what? 1 by 2 means 0.5 divided by R is what? Resistance. Resistance is 20 ohm. Resistance is 20. So what it will be the answer? Answer will be in something 25 milliampere something. So A, B, or maybe A or B. Let me just solve it. It will be simply 10 to power 3 into 10 to power minus 3, means it will be simply 1, 2, 3. So it will be 1, 2, 1, 2 and 25, means 25 milliampere. So 25 milliampere is the right answer for this particular question. Okay, done. Very good. A option is correct. So next thing, let me tell you one more question. Consider a long infinite wire carrying the time varying current. A circular loop of radius A and resistance R is placed with a center at a distance d from the wire. Okay, this is a good question. Find out the induced current in the loop. Suppose we have this long wire, and current is equals to I is equals to KT. Now we have a circular loop of radius A. Resistance R, which is placed with its center at a distance d, means there is at a distance d, and here the loop is placed. And what is the radius of loop? Radius is A. From the wire, find out the induced current in the loop. Done. Duration will be 1 hour to 1.5 hour, not that much. Okay. So first of all, let me tell you one thing. This expression, this thing, A is much less than D. This has a very big significance in this particular question or in this kind of questions. So first of all, if there is a current I is equals to KT, it means this is a time varying current. And if there is a time varying current, so because of this current, there will be a magnetic field, and which will also be the time varying, right? So first of all, we will calculate the value of time varying magnetic field. What will the magnetic field at distance d? So B will be equal to, B is equals to mu naught, formula is mu naught I by 2 pi r. So mu naught I by 2 pi d, correct? What is the value of I? So substitute mu naught KT divided by 2 pi d, correct? Now, this is the magnetic field at a distance d. Now we will have to find the induced current in this loop. So first of all, we will have to calculate the induced EMF. How will calculate the induced EMF? Induced EMF is equals to what? Minus d phi b by dt, right? Area is what? Area of this loop is pi r square or pi a square. But the magnetic field we have calculated at a distance d. Now, if this is the magnetic field at a distance d, it means this is the magnetic field at the center, right? Now, just listen to me very carefully that this is a wire and this is a loop, right? Now, this distance is d. So, magnetic field B is equals to mu naught I by 2 pi d. This is the magnetic field at the center. Now, if we have to find the total magnetic flux, it means magnetic flux passing through this entire area. It means suppose that if we are talking about this particular point, this particular red wala point, it means here the distance is something else. Suppose that it is x. So magnetic field will be at this particular point, it will be mu naught I by 2 pi x. So identically or ideally, the magnetic field is not constant in entire loop. So there is a problem. If magnetic field is not constant, then how we will write the pi b is equals to b into a, and if we want to write a is equals to pi a square, how we will write the magnetic field as the center wala magnetic field? So we cannot write this magnetic field. Understood? Okay. Last topic will be that particular self-induction and mutual induction. Okay. So B into A. Now listen to me very carefully. If you are trying to find the magnetic field at this particular point, it means you will have to think about something else. Now in this question, there is something else is given. This question, this expression, A is much less than D. It simply means that the radius which you are talking about, it very small. A is very small. It means you can assume that the magnetic field which you have calculated at a distance d, this will be uniform in this particular distance because A is much less than D. It means D is larger. It means if you are talking about this point or this point, it will not be much more change in the magnetic field. It means we can write this magnetic field for the entire loop. It means that we can write it here that d by dt, what is the phi b, mu naught kt divided by 2 pi d into what is area? Area is simply pi r square. So pi a square. Done. Now the question is solved. This was the trick. In this particular question. So now just solve it. Pi got cancelled. Mu naught k by 2d into it is 1 here a square. So this is induced EMF. Just neglect the minus sign because it is showing the direction, right? So what will be the value of current? I is equals to E upon R, just divided by R. So mu naught k a square divided by 2dr. This is the final answer of this particular question. So this is the trick of this particular question, that what you have to like assume that if A is much less than D, then the magnetic field which you are writing here, that will like transfer it in entire area of this disk, of this ring, whatever it is. Done till here? Any confusion, any doubt, you can write in the chat section. Chat section is only for you. Okay, let me move on to the next thing. This was about the magnetic flux and induced EMF, how we can calculate the induced EMF, how we can calculate the induced current. That is all about this thing. Okay, now next thing is motional EMF. Motional EMF is what? Suppose that we have a magnetic field. We have this magnetic field. It is all about like understanding these things. It is not about memorizing motional EMF. Motional EMF is all about feeling, that how you can feel it. Now let me tell you how. Suppose that you have magnetic field in this region and magnetic field is inside, as I have shown in the figure as well. So magnetic field is inside. Now you have a rod. Now you have a rod here rod, and it is hinged. It is hinged, right? It is hinged at this particular point and it is rotating with angular velocity omega. Okay, the length of the rod is L and it is rotating with omega. Now the problem is there are two kind of motional EMFs. Secondly, suppose that one is this case. Secondly, suppose that the rod is moving. Suppose that the rod is moving with velocity v, same length L. So there are two cases. There are two cases. One, the rod is simply moving in the magnetic field. Secondly, it is rotating in the magnetic field. It is rotating in the magnetic field. Okay. So let me tell you one thing. If you are, first of all, let me talk about this case, that if it is simply moving in the magnetic field. Now, just feel it, that if this is a magnetic field, can you see this particular thing? Can you see this pen? Okay. I think you can see this, right? So if this is the magnetic field, or just talk about my hand. Okay. This is the magnetic field. If this is the magnetic field and this is the rod, and if you want to like cross this rod, it means you'll have to cut this magnetic field. Like if you will cut this magnetic field, you can cross. It means if the rod is moving, it is cutting the magnetic field. It is cutting the magnetic field, right? Now listen to me very carefully. That if it is cutting the magnetic field, it means we can say that velocity is in this direction. So electrons are also moving in this direction. So V cross B, B is inside. So positive charges will be upside and negative charges will be down. Simple. Because so if it is a metallic rod, it means electrons, positrons, whatever it is, positive, negative charges are moving in this direction. So if V is in the direction, we know the force on a charge F is equals to QV cross B. QV cross B, right? So if a rod is moving in this direction, it means all the charges are moving in this direction. So we can say V cross B means force is upwards. Magnetic force is upwards. It means positive charges will be upward. This is positive and this is negative. It means there is a electron separation, positive charge or negative charge separation. It means positive charges are upwards and negative charges are downwards. It simply means that here is some potential difference between positive and negative charges. This potential difference is called motional EMF. This is called motional EMF. It means here we can write I'm writing directly the formula of magnetic field. Motional EMF. What is motional EMF? E is equals to, or we can simply write motional EMF is equals to motional EMF, that is equals to what is the velocity? Suppose the magnetic field is B, length is L. Okay, so motional EMF is V cross B dot L. This is the formula of motional EMF. And if we talk about the magnitude of motional EMF, magnitude of motional EMF is simply BVL. BVL. If all the things are like suppose that this angle B and V are also perpendicular, and this particular like B and V are like perpendicular, and this is the also something. Suppose that this is V and this is B, like this is V and inside the B. So if they are perpendicular, you can simply write that this is 90 degree. It means it will be the maximum. It will be the maximum. So force is upwards. So B cross V is in this direction, and if L is also in this direction, so then the motional EMF is maximum. This is like the simplest case of the motional EMF. This is the simplest case of motional EMF. Done till here. So this is BVL. Similarly, if we have this rod, and it is rotating in the magnetic field. Okay, it is rotating in the magnetic field like this. So I'm going to tell you how we can calculate the motional EMF in this particular case, because the questions are being asked from the middle of the derivation, right? So suppose that it can change the scenario. So you'll have to learn how to calculate this motion limit for a rotating rod. So suppose the length is L and it is rotating with omega. Suppose the length is L and it is rotating with omega. Now we will have to calculate the value of motion limit, right? Okay. Okay, done till here? Okay. Now listen to me very carefully. This thing. Listen. Now I have no idea. Okay. So first of all, this is a rod and this is rotating. Like this is rotating. And if this is rotating, I will not swing it too much. Okay. So this is rotating. Okay. This is rotating like this. So if it is rotating, it simply means that it is also cutting the magnetic field lines. It means, suppose how we will calculate, we will simply calculate, we will go on the x and take the element of dx. We will go on the x and take the element of dx, and it is moving in this direction with velocity v is equals to r omega, means x omega. So we can write the part of this, or the motion EMF produced in this small element, the small motion EMF, that is equals to, what is the formula? BVL. So v is what? X omega, and what is the length of this element? This is dx. So just integrate it from 0 to L. This is the catch. If you have a question in which it is saying it is rotating like this is the rod and it is rotating like this about this point, so you will have to take the limit from minus L by 2 to plus L by 2. The play is all about the limit. Okay, so just substitute it. B omega x means x square by 2 means L square by 2. So this is the formula of motional EMF in a rotating rod. Okay, done till here? Any confusion? B omega L square by 2. Okay, now suppose that there are some questions around this. There are some questions around this which are being asked regularly. Suppose that this is a current carrying wire which has some current I, and from this particular wire there is a suppose this loop of distance A or side A, and it is moving in this direction. It is moving in this direction. Okay, now we will have to calculate, or some, let me take the loop, just a rod of length A. Just a rod of length A, and it is moving in this direction. It is moving in this direction. Now we will have to calculate the value of motional EMF in this particular rod. Here the magnetic field is there, na? Because this wire has current in this particular direction, so magnetic field will be inside. So first of all, let me tell you one thing, that the formula we have derived, this formula, here. The formula we have derived, BVL, this is simply when the magnetic field is constant, and secondly, velocity is also constant, length is constant as it is. So, but in this case, velocity is constant, length is constant, but magnetic field is not constant, right? So, if the magnetic field is not constant, it simply means we'll have to think about something else. Suppose, how we will tackle this particular problem? Listen to me very carefully. This is the rod, or let me draw some bigger rod. So this is the rod. Now, how we will calculate? We will simply go on the x and take the element of dx. Why we are doing so? Because the magnetic field is not constant for all the points. Because if you will go away from the wire, the magnetic field will be decreasing. At a particular point, magnetic field will be constant. But as we go further, the magnetic field will change. Definitely. Okay. Now, at this particular distance x, the magnetic field will be B is equals to mu naught I by 2 pi x. Now we have to write the motional EMF, right? So first of all, this is moving with velocity this v. Okay, so we can write the motional EMF dE, small motional EMF dE, that is equals to what? Formula is BVL. So B is what? Mu naught I divided by 2 pi x into velocity is v, and what is the length of this element? Length of the element is dx. So just integrate it. Now the problem is solved. Now you just have to put the limits. Limit is from a to 2a, because it is starting from here, means x is equals to a, and it will complete till here. So a plus a means 2a. So limit is from a to 2a. Now just solve this. E is equals to what? Mu naught I by 2 pi. What is the integration by of 1 by x? It is ln x. Limit from a to 2a, just substitute the limit, mu naught I by 2 pi ln 2a by a means simply ln 2. So mu naught I by 2 pi ln 2, ln 2. Done. Any confusion till here? Done. Okay, next thing. Now since we have learned this thing that if a rod is moving or rotating in a magnetic field, it has some motional EMF, right? Now the problem is that if a rod is moving like this, okay, we can do something else with the rod. Suppose that this is the rod, this is the rods, right? These are called rails, okay, and these are kept in some magnetic field, and these are infinite rails, and there is a rod which can slide frictionlessly on these rails. Understood now? Like some rail, train, or okay, good. So if this is a rod and it is moving in this direction with velocity v, now this rod is connected with some external circuit. Suppose that like this rod is connected with some external circuit like this. Done. Now if we are moving this rod in this particular direction, this length is L and magnetic field is B. So we can write that there will be some as I said earlier, that there will be some motional EMF in this particular rod. So if it is moving in this particular direction, there will be some motional EMF. And what will be the direction? Since V cross B means force is upside, positive charge is upside, means battery will be like this, means positive charges are upside and negative charges are downside. So you can assume it as a battery which has the voltage E is equals to BVL or VBL, right? This is a battery of voltage VBL. Now we have to calculate what if this resistance is R, what is the current flowing through this R. This is a very major application of the motional EMF. This is a very major application. Why? Because if we are just what we are doing, that we have just this rod and we are just pulling this rod with velocity v. So we don't have any electrical energy. We didn't give any electrical energy. It means the electrical energy is being produced by the help of our mechanical energy. So this is an application in which the mechanical energy is being converted into the electrical energy. This is a very important application of this motional EMF. So now since the motional EMF of VBL is being produced, it means we can simply write the current flowing through this particular resistor is equals to E upon R, means VBL divided by R. Now one more thing. In the questions, it can give you a complicated circuit. It can just make it with the help of current electricity plus EMI, means this motional EMF plus current electricity. Very important circuit is connected here. Let me show you some problem. I must have some problem like this. Just look at this problem. What the problem is saying, can you is it visible? Yeah. The square middle wire loop of side 10 cm and resistance 1 ohm is moved with a constant velocity V0 in a uniform magnetic field with the magnetic induction of 2 Weber per meter square as shown in the figure. The magnetic field lines are perpendicular to the plane of the loop. The loop is connected to a network of resistance each of 3 ohm. Okay. The resistances of the lead wires OS and PQ are negligible. OS is what? OS, this is OS, and PQ are negligible, and the current what should be the speed of the loop, so that it has the steady current of 1 milliampere in the loop, right? Find the direction of current in the loop. Any confusion? Okay, listen to me very carefully. That find the direction of the current in the loop, and we'll have to also find what is the value of velocity, right? Now if this is a loop, just listen to me very carefully, as I have said that if the rod is moving, listen, just if the rod is moving, it simply means it will have some kind of motion, right? if there is some motional EMF, it means if it is moving in this direction, if it is moving in this direction, it means V is in this direction, V there, B inside, V cross B means positive charge is upside, negative charge is downside, means battery will be something like this, right? Now, what it is saying, the current is of 1 milliampere. Current is of 1 milliampere. It means if current is of 1 milliampere, it means 1 milliampere. Current is of 1 milliampere. Now, we have the resistance also. We have the resistance also. What is the resistance of this circuit? If this circuit, I'm just drawing it like here. So this circuit is something like this. Okay. 3 ohm, 3 ohm, 3 ohm. This is also 3 ohm. This is also 3 ohm. And circuit is connected here. Circuit is connected here. Don't confuse it because it is something. It is not looking like a Wheatstone bridge, but it is a Wheatstone bridge. Just 3 into 3, 9. 3 into 3, 9. And if ABL, remember R1, R4 is equals to R2, R3, means this is not valid. This will be negligible, right? The current through this particular wire will be negligible. Okay. Yes, we'll have to find the negligible resistance. Okay. We have to find. So now, if this particular wire is removed, it means simply the total resistance 3 plus 3 means 6. 3 plus 3 means 6, right? And this 6 and this 6 are in parallel. So 6 and 6 are 3. So the total resistance of this circuit is 3. The total resistance of the circuit is 3. Now, there is one more thing, that it is saying the square metal wire, metal loop of side 10 cm and resistance 1 ohm. There is also a resistance of 1 ohm in the loop. Means we can say if this resistance is total 3 ohm and loop resistance is, suppose that this is the resistance of loop, this is 1 ohm. So total resistance R total, that is equals to 3 plus 1 means 4 ohm. Means 4 ohm. Now, we have this total resistance. We have this total current. What is the current? 1 milliampere. So I is equals to what? 1 milliampere. Now, can we find the value of that particular motional EMF or EMF or voltage, right? So E is equals to what? E is equals to what? IR. IR. So I is what? 1 milliampere into resistance is what? 4. So E is what? 4 milliampere. Sorry, 4 millivolt. This is the induced EMF. Now we have the B, we have the side. Now can we find the value of velocity? Because E is equals to what? E is equals to what? BVL, and E is what? E is 4 milliampere, means 4 millivolt, means 10 to the power minus 3, that is equals to. B is what? 2. We have to calculate. L is what? 10 centimeter. So 10 into 10 to the power minus 2. 10 into 10 to the power minus 2. What is the value of V? 2 got cancelled. 2 got, here it is 1. So V is equals to 2 into 10 to the power minus 2 meter per second. Meter per second. Or we can say 2 centimeter per second. 2 centimeter per second. This is the answer. This is the answer. R equivalent is 4. 8 into the power. What is 8? What is 8? No. Nah. It will not be 8, nah. It will be 2. Just check the calculation once and tell me if my calculation is wrong. Okay. Should we move on to the next thing? Should we move on to the next thing? This is all about motional EMF. This is all about motional EMF, and this is very important application. Okay, no problem. No problem. Okay. Just look at this problem. Just look at this problem. A rod of mass M and resistance R is placed on fixed resistance less smooth conducting rails, and it is projected with an initial velocity u. Find its velocity as a function of time. Good question. If it is like projected with speed u, then how the velocity is changing? First of all, this is the problem. So this has velocity u and there is a magnetic field which is inside. So the induced EMF, we can say that E is equals to what? BUL initial. And one more thing. If it is moving in this direction, then this is the positive, this is the negative. So let me draw it further. This is the positive, this is the negative, right? So this will be, because it is moving in this direction now. So current which will be flowing like this, I, and this is the circuit, this is the R. So what is the value of I? I is equals to what? VBL na? So what is the value of V? Sorry, what I have written? Array, I is equals to what? E upon R. So E is what? BVL upon R. Upon R. Any doubt till here? Hello, hello. Okay, any doubt here? So this is the value of current, and now we have to calculate the value of velocity as a function of time. Now listen to me very carefully. If we have this current which is also changing, because V is not constant now. V is not constant. Now since the current is flowing, it means there is a force. Remember, F is equals to IBL sine theta. Remember, so if there is a current, it means there is a force. So F is equals to what? I is equals to what? B U L into BL divided by R, right? So let me write, at some instant the velocity is V. This is not the initial, at some instant it is velocity V. Velocity is a function of time. So F is equals to what? F is equals to ma, and that is equals to what? B square L square V divided by R. This mass just goes here, this mass just goes here, and this is dV by dt. This is dV by dt. That is equals to B square L square by mR into V. Now this is a function, and now we will calculate it. So dV by dt, that is equals to what? dV by dt, that is equals to, sorry, that is equals to what? That is equals to B square L square by mR. B square L square by mR into V. Right? Now calculate it. dV by V, that is equals to B square L square by mR into dt. Just integrate this. So it will be what? ln V, that is equals to B square L square by mR into T. mR into T. Now, since we have to put the limits as well, so initially at t is equals to 0, the velocity is u. At t is equals to t, the velocity is v. Now, so limit from u to v or 0 to t. So leave it here. So ln v minus u, ln v by u, that is equals to what? B square L square by mR into t. ln goes that side, it will be simply v by u, that is equals to exponential e power b square u square by mR into t. So v is equals to what? V is equals to u e power b square u square by mR into t. This is the expression. This is the expression of this particular question. This is the answer. Then, any confusion till here? Should we move on to the next thing? Definitely we should move on to the next thing. Okay? Now. Just give me a second. Now there comes induced electric field. Very good. L is in numerator. Let me check. L is in numerator. Where is L? Yeah, B square L square. Yes. B square L square. Correct. Okay. Now where I was at the induced electric field. So what is the induced electric field? Let me tell you one thing, that if you have a time varying magnetic field, then because of that time varying magnetic field, there is something called induced electric field. Okay. So let me tell you one thing, that we have already studied electric field, which was like in the electrostatics. Okay. And that was something which was originating because of a charge, right? But this induced electric field is generating because there is a time varying magnetic field. So just remember this expression or this statement, that a time varying magnetic field produces the electric field. So what is the expression? I'm not going to derive all the things, I'm just going to write the expression. Okay, so time varying electric field, so the integration of E dot dl, that is equals to, this is the expression, and that is equals to minus d phi b by dt. This is the expression of time varying electric field. Here E is what? This E is what? Induced electric field. This E is what? Induced electric field. Okay. So if we talk about how to apply this particular expression, okay, let me tell you one example, that what will be the electric field at a distance r from the axis of changing cylindrical magnetic field B, which is parallel to the axis of the cylinder. So this is a magnetic field which is B is equals to B naught T, and we have to calculate the value of magnetic field at a distance. Suppose that this is a wire, this is a cylindrical wire. Okay, just try to understand this. This is a cylindrical wire. Just give me 1 second so that I can show you. This is a cylindrical wire. Okay, now listen to me very carefully. This is a cylindrical wire, and this is the This is the cross-sectional area which you are seeing in this particular question. So now if this is a cross-sectional area and the magnetic field is inside, now we have to calculate the value of what is the value of electric field, induced electric field. So suppose that we are talking about the inside. If R is less than R, what is the expression? Close integration of E dot dl, that is equals to, it is similar to you have applied in the Gauss law, kind of something, okay, minus d by dt, d phi b by dt into this, right? Now phi b means the flux passing through this area. So E into dr is what? 2 pi r, that is equals to, phi b is what? Pi r square into b naught, or b is changing with time, so b naught t and d by dt, okay. It is simply basically pi got cancelled, 1 r got cancelled. Here E is equals to what? B naught r divided by 2. B naught r divided by 2. It means the electric field or induced electric field is increasing as time. Sorry, not increasing. It is constant. It is constant? Yeah, it is constant actually. It is constant with time, induced electric field. But if you talk about it is increasing with R, sorry, it is not increasing with time, it is increasing with R. If you go outside, the electric field will increase. But if we talk about the outside, means this is R is greater than capital R. If R is greater than capital R, this expression will be what? E into area of this loop is what? 2 pi R. That is equals to, flux will be what? B naught into T, differentiation is 1, and area is what? Pi. What is the flux area? This is the flux area, means pi capital R square. So pi again got cancelled. E is equals to what? Mu B naught R square by 2 small r. So it means the induced electric field is decreasing with R. Induced electric field is decreasing with R. So we can also draw the graph of it. If this is E, this is R, this is induced electric field, and this is decreasing with R. So this is R is equals to R. So this was all about induced electric field. Done till here? Next thing. Next thing is self-inductance. Now this is a very small thing, but it is a very important thing, okay. So self-inductance is what? If we have a loop in which some magnetic field is present, now if we change the current in that particular loop, suppose that this is the loop and this is current. So if we change the value of current, then it simply means there is some, just think about it, that because of this current, there will be some magnetic field, na? There will be some magnetic field at the center. But if we change the value of current, it simply means that this magnetic field is also changing. It means the flux through itself is changing. And if the flux through itself is changing, it means there will be some induced EMF. And because of that induced EMF, there will be some induced current as well. Okay? Okay, done? Okay, that I can't, how can I tell? Okay? Okay, done? So first of all, if this is a basically loop and the current I is flowing, so because just listen to this expression, that if we change the value of current flowing in a particular, suppose this is the loop, suppose that this is the loop, okay, suppose this is the loop, just think about this, this is the loop, and if we change the value of current through this, it means the magnetic field is changing, and if the magnetic field is changing, it means flux is changing. If flux is changing, it means it will produce another induced EMF, and because of that induced EMF, another current is being produced in this particular loop. So it means because of its own changing current, and another current is being produced in itself. So that is called self-inductance. That is called self-inductance. Any doubt? So it means as we change the value of current, the flux will change. The flux is directly proportional to the induced current. Okay, so sorry, the current. So flux is equals to what? We'll just simply put a constant here, and that constant is L. That constant is L, and this L is called self-inductance. Self-inductance. Okay, and this phenomena is called self-induction. Right? Now just differentiate it. So it will be simply what? d phi by dt. That is equals to what? L di by dt. So this is what? Induced EMF. E is equals to what? Minus L di by dt. This is the expression of induced EMF. This is the expression of induced EMF. Any doubt? Now, next thing. If we talk about the solenoid. Now, these are the applications of the something like if we have a solenoid and the current is changing If we change the current, what is the value of flux? So we'll have to simply write the magnetic field B is equals to what? B is equals to mu naught Ni. Now we have simply seen this expression. Phi is equals to Li. Now we can write the flux through this. So phi is equals to what? B into A. B is what? Mu naught Ni. Mu naught. Suppose the number of turns in are N. Number of turns per unit length, right? So B is what? Pi R square. B naught. Suppose the magnetic field is B naught. So B naught into area is what? Pi R square. And number of turns are what? N. So number of turns are N per unit length. It means we'll have to simply multiply by the L. So these are the number of turns per unit length, right? Now pi R square and L. This is the flux. Now we can write the here current is what? B is what? B is not B naught. B is not B naught. B is mu naught Ni. So B is what? Mu naught Ni into Ni mu naught Ni into this R square NL. Right? Where is pi? This is pi. So this can be written as mu naught N square. This is mu naught N square. Pi R square is what? Pi R square is area. Means this is volume. Pi R square is volume and multiplied by N. So this is what? Phi is equals to something into I. So this is not something. This something is nothing but L, and this is mu naught N square V. This is something is V naught mu naught N square into V. Got it? Any doubt till here? Any confusion? Should we move on to the next thing? Definitely we should move on to the next thing. Okay. So I'm just writing the formula of energy stored in the inductor. Just keep this thing in mind that if we have an inductor and current I is flowing, the inductance is L, then we can write the expression of energy is half Li square. This is the expression of energy flowing in a or stored in a conductor. Okay. Next is mutual inductance. What is mutual inductance? Similar to the self-inductance, there is a phenomena called mutual inductance. Suppose we have two loops like this. Suppose this is a loop, this is another loop. Very bad. This is another loop. And this radius is R1 and this radius is R2. So suppose we are changing the current in this particular loop, I1 we are changing. Right? So if we are changing the current in I1, there is a flux change in the second loop as well, because they are placed coaxially, right? So if we change the flux, if we change the current in the first loop, then the flux will change in the second loop. Now this is the expression of mutual inductance. So phi 2 is equals to M into I1. Here M can be written as phi 2 by I1. Phi 2 by I1. So this is how we write the expression. Okay. Hello. So now let me tell you one thing. Suppose we have two solenoids. We have two solenoids like this, or we have two loops. Suppose that we have two loops, and this is the radius A and this is the radius B. Now we have to calculate the mutual inductance between them. How we'll calculate? So first of all, suppose the current I is flowing in it. So if the current I is flowing in it, on the condition is B is much less than A. So we'll have to find the value of magnetic field at the center. B is equals to what? Mu naught I by 2A. Mu naught I by 2A. This is the expression of magnetic field at the center. So we can write the flux passing through this. Phi B, that is equals to, phi B is equals to B is what? Mu naught I by 2A into area is what? Pi B square, right? Now we can simply write it like mu naught I pi B square. This question is asked in the JEE Main examination for like 3 to 4 times or more than that. Okay. So this is the phi B. So we can write it like phi B, that is equal to this. So phi B is equals to what? Mu naught pi B square divided by 2A multiplied with I. So this is the expression of mutual inductance. M is equals to what? Mu naught pi B square divided by 2A. So this is mutual inductance. Any doubt, any confusion till here? If you have any doubt, you can write in the chat section. So what we have done in this chapter till now. Now you can see this question. This question was asked in the JEE Main examination as well, and we have already solved this. What was the answer? I think answer was something like mu naught pi A square by 2B something. You can check. We have just solved. So these kind of questions are being asked regularly, and what this expression signifies, B is much greater than A. As I've already told you that we are writing this expression of magnetic field B is equals to mu naught I by 2B. This is at the center now. this is at the center. And if we want to write the magnetic field or flux passing through this entire ring, it means we have to assume that this is very small, as it is like concentrated at the center as well. So this is the magnetic field which is signifying this particular expression. Done till here? Okay. So this was all about the revision of this chapter. So we have completely revised this chapter in around 1 hour, less than 1 hour. So that is it. I was planning to revise this chapter as less time, like in 1 hour, 1.5 hours. So we have done. So if you have any doubt, any confusion, if you're watching it live or watching it recorded, you can write in the chat section as well as comment section. So thank you so much for joining the session. We'll meet in the next session as well. So if you have any query, any feedback about any class, you can write in the comment section as well. So thank you so much everyone for joining the session. See you in the next class.